In this lesson, we will look at the controls and indicators for the hydraulic system. Firstly, those used on older aircraft, and then we will examine the indications given to pilots on the electronic screens used on most new generation aircraft. Large aircraft with multiple hydraulic systems need fairly sophisticated control and indicating systems. Shown here is a typical hydraulic control and indicating panel from the flight engineer's station of an older large airliner with 4 separate hydraulic systems, labelled A, B, C and D. A clear window may be fitted in the reservoir to provide a means of checking fluid level during servicing. The reservoir may also be fitted with a float-type contents unit, which electrically signals fluid quantity to an instrument on the hydraulics panel in the crew compartment. The reservoir low-quantity light will illuminate if the fluid quantity falls below a predetermined level. Fluid temperature is monitored by a temperature sensing element. If the temperature of the fluid in the reservoir becomes excessive, the high temperature light will illuminate. The firewall shutoff valve is used to shut off fluid at the pump inlet. Pulling the engine fire switch will close this valve. The flow bar is lit when the valve is open. Operation of the pump shutoff switch energizes the solenoid-operated depressurizing valve, offloading the pump. You will recall that operation of this valve blocks off delivery to the system, but allows pump cooling and lubrication fluid to continue to flow. There are air turbine motor-driven backup pumps in the B and C systems. The switches highlighted here control these pumps. The engine-driven pump case drain return fluid temperature is monitored in order to check pump condition. The lights highlighted here illuminate if the temperature becomes excessive. If the engine-driven pump outlet pressure is low, then a pressure-operated switch will illuminate the pump low-pressure light. Systems B and C have electric motor-driven hydraulic pumps, which are used to power the brakes when the aircraft is being towed. They are controlled by the switches shown here. There are 2 power transfer units. They use hydraulic motors in systems B and C to drive pumps in systems A and D respectively. They are controlled by the switches highlighted here. The ram air turbine is deployed when the switch highlighted here is pressed. It will power hydraulic system B, which is used purely for the primary flying controls and wheel brakes. The system has 2 brake accumulators. If the accumulator pressure is low, the lights highlighted here will illuminate. Large aircraft have electrically operated pressure gauges fitted on the hydraulics panel to indicate system pressure. Smaller aircraft may have a direct reading pressure gauge in the cockpit. In order to protect the system from leaks in the pipework to the gauge, and to prevent the cockpit from being filled with hydraulic fluid in the case of a leak, a pressure relay is often fitted in the line. The pressure relay consists of a cylinder with a free-floating piston inside it. System pressure is fed into one side of the piston with the other side being connected through a pipe filled with fluid to the gauge. System pressure is transmitted through the piston to the fluid supplying the gauge. In the case of a leak in the pipework to the gauge, or in the gauge itself, only the fluid between the pressure relay and the gauge will be lost. Direct reading gauges are often fitted to accumulators and reservoirs to enable servicing operations to be carried out. Warning of overheating of electrical motors, which are used to drive backup emergency hydraulic pumps, may be provided by fitting a temperature sensing element in the casing. In the event of a motor overheat, the warning light will illuminate. In more modern aircraft, hydraulic system information can be viewed on electronic screens. The system is normally configured so that in the event of a failure, a warning will be enunciated, and the relevant page will be automatically displayed. This diagram shows an electronic screen from an Airbus aircraft, displaying the hydraulic system configuration and indications. There are 3 independent systems. They are identified as the green, blue, and yellow systems. Reservoir quantities are graphically displayed here. The indication is green unless the reservoir level is low, when it changes to amber. These boxes indicate pump status. They show in line for a pump which is operating, and cross-line for a pump which is not. System pressure is displayed at the top of each system. The ram air turbine and the power transfer unit configurations are also displayed. The flow arrowheads are empty when they are not operating, and filled green when they are. Here is a typical hydraulic control panel from a modern 4-engined aircraft. As you can see, it is much simpler than an older aircraft. However, again, there are 4 separate systems. The push buttons control the engine-driven pump depressurizing valves. They have pump low-pressure lights integrated in them. The rotary switches control the electrically or pneumatically powered backup pumps, with their respective low-pressure lights above. You will notice that the number 4 system switch has an extra position marked AUX. This position is used to operate a low-volume electrically powered pump to pressurize the brakes prior to engine start or when the aircraft is being towed. Each system has a master fault light. The cause of the fault can be found by checking system status on the electronic screen. You should now be familiar with the control and indicating systems used on old and new generation airliners. Here is a complete hydraulic system, showing many of the components we have discussed. To review any component, you may click on it.